Hi, my name is Dr. John Chick, and I'm a professor in the Department of Chemistry and Physics at Mount Royal University. I would like to describe to you some of the instruments that are available at Mount Royal University. These are the Agilent Cary 50 UV visible spectrophotometer, the Agilent Cary Eclipse fluorescence spectrophotometer, and the Thermo Fisher DRX Raman Microscope. These three instruments exploit the unique properties of molecules to absorb and release energy as a way of determining what compounds are present and their amounts. The energy that I'm referring to is in the form of light, both what we can see and what we can't. As you all know, white light, like that from the sun, is composed of many colors as seen in a rainbow after a rainstorm. Each of these colors has a specific energy associated with it. Molecules characteristically absorb certain energies, which manifest as different colors. And we can use these colors, these wavelengths that we'll talk about later, as a way of identifying the compounds as well as measuring their amounts. So I have two lasers here. I have a red laser and a green laser. Let me just show that to you right now. So you can see the red laser there on the screen, and I'm going to just show you the green laser, which is quite a bit brighter. So you can see the green laser right there. Okay, so just kind of remember the intensity. Now in this little plastic bottle, I have a red beverage. I think it's cherry Kool-Aid. And what would happen if I shine each of these laser lights through this liquid? Think about what would happen if I shine the red laser light or the green laser light through this. All right, so think about it for a second. All right, let's go see what happens. So I'm going to now shine the red laser through this, right? And I'm going to now remove the bottle. And you can see that really, except for a position change, the intensity is, well, a little less, but not really noticeably less. However, if I go ahead and I use my green laser, you can see that there's the green laser going through that red Kool-Aid. And when I remove the bottle, you can see how much brighter it is. Going through the Kool-Aid and out, no Kool-Aid. So it's as if the colored molecules in the Kool-Aid prefer to absorb green light over red light. This is the concept of absorbance. If I had thousands of lasers, each with a slightly different color, I could test each one of them and see how the molecules differentially absorb those different colors of light. And the first machine that I'm going to show you, the Cary 50, does exactly that. And that produces a unique profile for that molecule, and we can also use this information in order to determine the amount of that molecule in solution. The Agilent Cary 50 UV visible spectrophotometer allows you to select particular colors of light as measured by wavelength. Expose a sample to that wavelength of light and measure the amount of light being absorbed. The instrument can also be configured to automatically change the wavelength of light falling on the sample and at the same time measure the absorbance of that light. This allows the machine to return a spectral profile of the compounds in the sample. Let me show you how this works. This is a yellow highlighter, and I'm going to dip the tip of that into this little tube of water. And hopefully, it will slowly start to color the water, and it's getting a little darker and darker as the ink from the highlighter is dissolving into the water here. I think that's probably enough right there. Now I'm going to go and put the sample into the Cary 50 by transferring the liquid into this cuvette, and then we will take the spectra of this. So now that the sample is loaded into the spectrophotometer, I'm just going to set up a data collection run. I'm going to hit the setup button here. And what I'm going to do here is I am going to set the starting wavelength and the ending wavelength, the start and the stop. And what I'm going to simply do is I'm going to start at about 700 nanometers, which is red. And I'm going to stop it at about 400 nanometers, which is blue. We don't have to really deal with most of the other controls here. The most important one is to select how fast the data is going to be collected. The slowest setting will give you the best data. However, it takes the longest. If you just want to take a quick look, what we're going to do for this video is I'm simply going to hit medium. And now that's all set up. I'm ready to go. I simply hit the start button and I save it to a file. I'm just going to call it highlighter, and away I go. And this is sample 1. And as you can see, it's marching through the wavelengths right here, going from the 700 and it's heading towards the 400 nanometer wavelength. Now, before we shot this, I had already collected a background spectra, which is the cuvette and the water by itself. And so what you'll see ultimately is the spectra of just the highlighter without the water or the cuvette making any contributions. All right, so now that we have the spectra, let's take a look at the results. As you can see, there are two rather prominent peaks in the absorbance spectra. There's one at about 453 nanometers, and there's another one at about 400 nanometers. You can see that these are the two colors that were largely absorbed by that highlighter ink. And you can see that way out to here, there's almost nothing. So you can see that there are really two prominent bands that the highlighter ink was absorbing. At Mount Royal University, we also have a number of accessories for the Cary 50. Inside the instrument, there's a temperature-controlled sample holder for up to 18 cuvettes. Temperature control is very important when monitoring chemical reactions that generate colored products. Measuring the speed of this product formation and how it is affected by temperature and other solution factors reveals a lot about the mechanism of the chemical reaction in question. In further support of this type of investigation, Mount Royal University also has a stop flow mixer, which allows us to mix two reactants very quickly and then start the collection. With this setup, the Cary 50 can measure events as short as 12.5 milliseconds. In addition to absorbing light, many compounds will take this energy and produce light of a different color. It's like the molecule absorbs blue light and emits red. This fascinating process can be further classified as fluorescence and phosphorescence, depending on the details that are not really important at this moment. The next instrument I'm going to show you is designed to study this and other fascinating phenomena. Like the Agilent Cary 50 UV visible spectrophotometer, the Agilent Cary Eclipse fluorescence spectrophotometer allows you to select the wavelength of the light that falls on the sample. I will refer to this input as the excitation. However, in addition to that, the Cary Eclipse can also scan the light produced by the sample. The light generated by the excitation light is called the sample's emission. Like the Cary 50, the Eclipse can be set up to automatically scan either the excitation light or the emission light or both simultaneously. Probably the most common mode used in the Eclipse is to fix the excitation light at a specific wavelength and then collect the resulting emission across a range of wavelengths to generate the sample's emission spectrum. For a demonstration, I'm going to collect the emission spectra of the yellow highlighter ink that we already looked at in the Cary 50. Fluorescence is much more sensitive than absorbance, so I have already diluted the highlighter ink quite a bit. Now, from the absorbance spectra, we know that there is a maximum absorbance at about 453 nanometers. This means that the compound in the ink absorbs the most light at that particular wavelength, and it would be a good place to put the excitation beam. Now, I'll show you how this is done in software. So I'm putting the sample into the holder. Now, What's interesting about the Eclipse is that there are two windows. So the excitation beam will come horizontal, while the emission beam will come up in the vertical direction. And you can see actually the two windows here. So now that I'm in my software, I'm going to simply start the setup. I'm in fluorescence. I need to select the emission. I have an option to go either excitation or emission. I'm going into emission. I'm going to set my emission. Now I'm going to set it just a little bit to a slightly smaller wavelength of about 450 versus 453. That's for practical reasons. And then I'm going to set my starting wavelength at 460, and I'm going to stop at about 650 nanometers. Now, one of the additional two things that you can set in this instrument that is not in the Cary 50 is I can set the slit width and also the scan speed, as you heard before. These essentially set the resolution and the time it takes to take your sample. So for this sample, I'm going to set up at 2.5 nanometers excitation window. I'm going to set this at a 5 nanometer emission window, and I'm going to just select a medium scan rate. The last important detail in this machine is I also should be aware of my PMT detector voltage. The PMT is the photomultiplier tube, and it's the thing that makes fluorescence very sensitive. It can amplify very low levels of light. And so what I'm going to do is set it to medium. I'm going to be there, and then I am all ready to go, and I'm simply going to hit the start button and go ahead. So you can see that's collecting the wavelength. You can see that there is a very strong peak in the fluorescent profile. And it's just going off here. You can see there's very little at the end. And there we go, we are done. So just looking at this, you can already see that there's a very strong emission peak at about 510 nanometers. That is, I put in about 450 nanometer light, and I come out with about a 510 nanometer light coming out at the other end. And so that's the process of fluorescence. So in addition to fluorescence and phosphorescence, the Cary Eclipse can also study chemiluminescence, which are chemical reactions that produce light, like fireflies do on a summer's evening. Like the Cary 50, there is also a temperature-controlled unit in here too, as well as the stop flow instrument can also be operated from within this equipment. We also have polarizers for measuring fluorescence anisotropy, which is a means of measuring the tumbling of molecules in solution. So in certain key ways, the thermoscientific DRX Raman Microscope is similar to the Agilent Cary Eclipse fluorescence spectrophotometer. Both instruments irradiate a sample with light and then measure the resulting emitted beam. However, whereas in fluorescence, molecules appear to have a preferred route for channeling the absorbed excitation energy into an emitted beam of light. Raman spectroscopy, however, measures the small amount of light that is different from the original excitation beam. Think of it as this ball. If I drop it from a certain height, it should ideally return back to exactly the same height. But because of air resistance and imperfections in the rubber, the ball doesn't quite return. When a molecule absorbs incoming energy and there is no convenient route to emit this energy, like in fluorescence, the vast majority of that absorbed energy is emitted at the same wavelength. However, like the ball, a small fraction of that emitted energy is also slightly different in light color. This is the Raman effect, named after the Indian physicist C.V. Raman, who was awarded the Nobel Prize in Physics in 1930. These small differences in energy report different vibrational modes between atoms in the molecules, similar to infrared spectroscopy. What also sets the DRX from all our other instruments is that, well, it's a microscope. You may have noticed that for the Cary 50, the Cary Eclipse, and our other instruments, the sample had to be prepared. It had to be placed in solution, put into a cuvette before examining it. However, the Raman microscope has the ability to focus on a particular part of the sample. So right now in this machine, I placed a little piece of paper on a cover slip, and I place it in the machine, and now I'm going to look at particular pigments in that piece of paper. So if I head towards the spectrophotometer and I pull out the correct window, you can see that you see the paper, you see the fiber in the paper, and you see little blue dots, because this is a piece of blue. This is some blue ink. And I can simply, by moving the joystick around, I can change where I'm looking at on the instrument. I can focus on this, what I think is a particularly interesting blue speck, and I can say, all right, I'm going to simply go and let me just check my instrument, make sure that I'm collecting what I need to collect. You can go to the setup mode, and then you can say, I can set here things like the wavelength. I can set how much power, how big is the beam. There are various parameters that I can set here, which are very important to have. So once I'm satisfied with the results, I just simply go and collect the sample, right? Now it's going ahead and collecting the sample, and it takes a bit of time. The advantage of this microscope is that I can look at a sample that has what I think are many different samples. Let's say I have a piece of paper and I see there's some black specks on it. Is the black specks gunshot residues? Are they ink? Is it pencil lead? Right, I don't know, it's all black. But with this microscope, I can simply put the whole piece of paper or a piece of that paper under the microscope and interrogate each spot and say, well, what is this spot? Collect its spectra and then compare it to a database. This is extremely powerful tools, especially in the field of forensic medicine and forensic sciences. You have a paint chip at an accident scene. Well, it's a pretty small paint chip, but you can put it under the microscope and you can figure out what car it came from. The RCMP and other law enforcement agencies have enormous databases of all pigments from all models, from all years and makes. They can easily match this particular paint fleck to a particular car that was at that accident. This makes this particular technology extremely powerful. And that's why you'll often see it now being used in police crime labs and other such places. Another application we have at Mount Royal is people in geology want to look at various crystals within a rock. Well, the rock has a lot of different crystals in it. So I can look at each crystal and say, well, what is this crystal? People in anthropology have used this to look at pigments on pots. What is the red pigment from? What is the blue pigment from? If you understand what the chemical makeup of those pigments are, maybe they tell you something about trade. Maybe you realize, well, this red pigment doesn't come locally. It comes from somewhere that's, hundreds of kilometers away. And so you begin to build up various interesting information from this particular instrument.